All right. So thank you. The lead author of this paper couldn't be here, so I'm giving the talk. Tianran Wu and Tobin Munsat are co-authors on this paper. This is about dust dynamics and the transport of small material in a binary asteroid system. All right. So as during this session several times, this ongoing DART mission was mentioned, which is an impact experiment changing the trajectory or the orbit of the small secondary asteroid going around the primary one. These are tiny bodies. Even the bigger one is only, sub-kilometer, 780 meters in diameter, and the tiny one is only 160 meters in diameter. The noteworthy fact on this plot is that the little guy goes on a retrograde orbit. So it's a head-on collision with the impactor. All right, just one push at a time. So, in the recent visits to asteroids, we were all mesmerized with the surface topology and the characteristics of these bodies. And perhaps to us, certainly to me, because I'm not an expert, is the lack of small dust particles on these surfaces. So it seems that the structure is kind of ending on millimeter and centimeter size, and the smoothing effect of even smaller dust particles seems to be absent. Certainly that was the case on Bennu, Osiris-Rex, and Hayabusa, as well, visiting tiny asteroids in the solar system. To us, what is interesting is try to reproduce the conditions these surfaces or bodies experience in space. On the left is a laboratory experiment where we show you electrostatic dust lofting. You could do this with a pile of dirt. Actually, as far as laboratory experiments goes, these are big particles, 50 to 100 micron radius dust particles, and you could make them move around simply by shining UV or shining an electron beam. What is important that whatever you do, you have to produce secondary electrons. As it turns out that charging of a regolith is very different than a single object setting on a surface, and the subsurface structure plays a very important role. What should be taken from here is as a function of dust particle radius. These are the initial launch velocities, kind of modest. It's 11 divided by the radius in microns, meters per sec. So, sub-meter per sec. But what you have to remember on these tiny objects that are kilometer across or less, this is actually exceeding the escape speed. Just by shining the sun shining on these surfaces, being exposed to the solar wind flow, electrostatic processes can simply remove tiny particles from the surface. Oops. Oh, all right. I will learn. By the end of this talk, I do well. So on the right is an evolutionary model of what happens on the surface of an asteroid as you start removing small particles. This is a Monte Carlo simulation that involves a lot of moving parts, a lot of bits and pieces. What happens when you have impacts? What happens when you have thermal fatigue? What happens when small population of dust particles no longer cover up the big ones? So to the best of our understanding, we try to write down a nicely coupled ordinary set of differential equations, the production of loss of particles of various sizes. Perhaps what was surprising that the removal of tiny particles actually shortens the lifetime of the big ones because they are no longer there to protect them against thermal fatigue, for example. So that's a recent paper, actually just came out a week ago or so, which tells you all the details of what happens and how quickly you could remove fine dust from the surface of a small asteroid. And it turns out that half a million year or 0.2 million year is sufficient to clean the surface of these target asteroids. There will be no small dust particles. If you were to look at them one at a time. Let's see. All right. So now imagine that both of these objects are launching dust particles. Where do they go? So their escape velocity their speed is high enough to escape the object, but now there is a fair chance that they're going to hit the other one. So I'm only look at today launching small particles from the bigger objects and see if it lands on the tiny one. We are, including gravity of the primary and the secondary and radiation pressure, and that is all for the time being. And we simply launch particles with the speed according to our lab measurements, and that's another discussion, and we could certainly, I'm happy to engage, is the generality of the speed distribution from the lab and its applicability to space conditions. And I stand by to the best of my understanding and believe that that is actually carries over. So the grains are, we launch them, a lot of them, in the size range of 1 to 100 micron, and then we follow their trajectories. All right. Here it is. And of course, as this binary system is moving closer and further away from the sun, the relative contribution to the perturbing forces, radiation pressure, is changing with 1 over r squared. So close to the sun, there is a stronger force, and further away, there is a lighter force due to radiation pressure. At aphelion, when you are far away, there are these strange long-lived orbits. And you would say, I've never seen anything like this. And of course, you might have, should you look up, for example, the hydrogen corona of the Earth or perturbations of ring particles. If radiation pressure is acting with gravity, the perturbation is such that you have these nice looping orbits. If you were to do plasma physics and have electric and magnetic fields, the orthogonal forces give you E cross B drift. So that's the same sort of physics. The particle is, well, I don't have a pointer, but the particle starts on the bigger red objects, makes a couple loops, and eventually hits in the backside of the little object. If you were to do this experiment closer to the sun, you either directly hit or very quickly hit from the big object to the small one, or you are actually escaping from the system. So you could launch a lot of these. Okay.
There's about 3 minutes left.
Thank you. And you make a map. Where do they land it? And here is the map. If you were close to the sun at 1 AU, there is roughly an even distribution of the leading and trailing hemisphere of the small object Didymos. If you are doing it further away from the sun at aphelion, 2.3 AU, there is an asymmetry between the leading and trailing hemispheres. The typical speeds and the efficiency of collecting them, you could imagine it's not very high. A fraction or a few percent of the big, the dust particles leaving the big objects might end up landing on the small ones. The speeds are kind of modest, 10 to 100 centimeters per sec. The radiation pressure, the gain or gravity is conservative, so the amount of energy gain or loss from gravity is minimal. Radiation pressure doesn't have a long time to act. So this is more or less reflecting the initial speed distribution as they were launched from the surface. Other than, of course, radiation pressure does matter at the end a little bit. So if you are impacting at 1 AU, the speeds are somewhat higher than at 1 AU are somewhat higher than if you were to have these impacts further away. And I believe my last slide, if you is here. Before I tell you the summary, the top right, first of all, the bottom right are example trajectories. They could be incredibly complicated. They can span days and days in orbit, eventually get lost or hitting one of these objects. On the top is kind of a summary where the study lands, which is the launch escape versus escape ratio on a log scale, and the mass ratio of the primaries, and what fraction of the dust particles will land from the big one to the small one. Yes, we can play with inclination. I mean, this study can go endlessly. There's a large number of knobs to turn, but we're going to sort this out. But what you should perhaps remember that electrostatic forces can remove small particles in an incredibly short amount of time. Normally, the leading hemispheres would be where it will be deposited on the small objects. So we are predicting a difference even in spectral properties of leading and trailing surfaces of the small bodies going around the big ones. This deposition pattern is kind of complicated and might change with distance to the sun. And, depending on the size, depending on the orbit, you will generate these patterns then if you were to take your spectrographs, hopefully it will show up in your measurements or the images you are taking. So there's a lot of calculations yet to be done and summarized, but here it is. These targets of future exploration, the small objects might have kind of interesting relations to plasma physics, interesting relations to the outcome of the plasma physics, how their surface properties will change and evolve with time. Thank you.
Are there any questions in the room? Oh.
Dan Britt, University of Central Florida. Hi, Mihayl.
There was one online first.
Okay. Umberto, I will yield to you.
Yeah, as you should.
I have been doing it all my life. I respect age.
Humberto, do you want to just ask your question?
Yes, I did online. You guys should read them.
Okay. The question from Humberto. Any ideas about this effect and the dramatic differences between the surfaces of Itokawa and Bennu?
I believe so. In fact, the last point is that we would like to extend it to other systems and try to make these arguments. What is the landing pattern? What's the production pattern of from the various objects? What happens on a single asteroid, being recollected versus escaping, the rotation rate. There's a lot of parameters to go through, but we would certainly like to take a look at Itokawa and Bennu and have anywhere where we have data in hand, we try to argue that these nice, cute little plasma process might make a difference.
Thank you, Mishi.
Kind of to follow up on that question, what materials did you use in your experiments?
Some of your dirt.
Okay, what I make lots of different dirt.
All right, I apologize. I might not remember, but we certainly have at hand MLS1 and GSC1 and GSC1A and some from your lab.
Okay.
And
my thought here is that the effect might be much stronger in highly polar minerals, such as what you get on Bennu and in serpentines, versus less polar things like you get in Itokawa, which are olivine pyroxene.
Since our background is not, planetary science, and I don't even know all the words you just said,
I can provide an annotated guide.
In my mind, fundamentally, the biggest difference is conducting versus non-conducting materials.
Yeah, I think that's...
How do you share the charge with your environment, and how do you charge?
Yeah.
So, but you're absolutely right. In the next level of details, the exact makeup of the material and the surface properties of little grains all play a role.
Okay. Very good.
I'm fascinated by the aphelion-perihelion difference because, and that makes sense, but it goes through those regularly. So how do they accumulate over decades?
Decades and centuries. If anywhere in the solar system you have an asymmetry, you will, and then somewhere else that is the deposition is symmetric, you don't bury the previously deposited material, you just add to it. So I think the asymmetry persists.
So which one rules, the aphelion or the perihelion?
So typically you spend much more time further away.
Okay.
So
Okay,
on the other hand,
I
much more
gotcha.
time
Okay.
further away, the processes are somewhat...
Okay.
The short answer is that I don't really know, because all the charging, all the solar effects are vanishing, but you are spending more time there.
Yeah.
The impact rates are changing. The further away you are, the slower the impacts, less of them happens. So I think the answer will come from Tianran or Professor Munsat's graduate student running through and turning all these knobs and go through instead of a snippet in time, pointing out that this effect is real and important, run through centuries or decades worth of deposition.
Yeah. Cool.
Thank you very much.